Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about how to set up a rate law. And we're going to talk about the differences between zero order, first order, and second order rate kinetics, as well as the half-life of a first order reaction. So let's get into this video. So the first thing in this video we're going to talk about is how do we set up a rate law. So in order to study kinetics, you have to remember you've got to do an experiment. You've got to design an experiment. So you're going to need some way to detect your experiment, whether you're detecting the reactant going down or the product forming by color change or absorbance or UV emission or pressure values. You're going to have some way to detect these compounds. And then what you're going to do is you're going to keep everything constant and then vary only one compound at a time and see how the rate is affected. So here's an example of a set of data with 6 different experiments that were set up to find the rate law of ammonium ion reacting with nitrite. So what you're going to need to do is you're going to need to keep the concentration of one of them constant and vary the other. Well, when we keep the concentration of ammonium constant, we could see that the other one, nitrite, we're going to double it. And each time that we double this, we could see the rate also doubles, which means the exponent is a 1. If we put something into the equation, like a 5, and we get a 5 out, and then we put a 10 in and get a 10 out, that's to the first power. So we call this first order with respect to ammonium. Well, then we're going to hold ammonium constant, and we're going to vary the other one. And we can see when we double nitrite, the rate also doubles, so it's going to be first order with respect to nitrite as well. So in order to set up a rate law, all rate laws are going to have rate equals K, which is called rate constant, time the concentration of whatever it is you're studying to whatever power, times whatever other thing to whatever power. So in this case, we have rate equals K times concentration of ammonium to the first power times concentration of nitrite to the first power. We can find K then by plugging in one of the experiments to this rate law. So say we just take experiment 1, all you're going to do is plug in the rate value for rate. You're going to plug in the 2 concentration values from experiment 1 in for each of the concentrations, and then solve for K. So it's just algebra 1. Once you have K, that's going to be, as long as you're at the same temperature, the same value of K. So you can find the rate at any concentration for these things. The only thing that's going to affect K, or the rate constant, is going to be temperature. So rate constant is temperature dependent, so be careful with that. You're going to want constant temperature. And the rate constant is helping you simplify the units so that your rate is only in molar per second or torr per second or whatever concentration per second or unit time that you're trying to find. So we could see based on our rate law, we're going to have things either to the 0 power, the first power, or the second power. That's going to be the most common in general chemistry and AP chemistry class. 0, first, and second order overall. So if we're thinking about first order, which is going to be rate is equal to K times concentration of whatever it is, A, to the first power. And then we're going to try to get to our integrated rate law, which is on most AP chemistry formula sheets. So if you remember from the previous video, rate is equal to the change in concentration over the change in time. And we just saw rate is also equal to K times concentration of A. Since both of these things equal the rate, you could set them equal to each other. Then we're going to rearrange and get all the concentration data on one side and everything else on the other side. And now we're going to do some calculus. And it's okay if you haven't taken calculus. Just like the previous video, I tried to teach you what a first derivative was without taking calculus. It's the line tangent to another line. So you have a curved line and you're trying to get a flat line off of that curved line. That's a derivative. We're going to do the opposite now, called integration. So we're going to perform this magical calculus integration, and our output for first order kinetics in order to linearize our data is taking the natural log. So when we get our final values, or our final output of this equation, we've got natural log of A is equal to negative KT plus the natural log of A sub naught. And A sub naught just means the initial concentration. And if you look very carefully, this should look pretty similar. It should look like your algebra 1 class, y equals mx plus b. So this is the slope-intercept formula, where you're going to have some slope, which is the rate constant. You're going to have your initial concentration, which is your y-intercept or your b value, and then you're just varying either the time, and then you're seeing what concentration happens after that time. So the whole point of doing this is to figure out what is the order of your reaction. You're going to have to do it, collect this data, and then plot your data in Microsoft Excel or maybe a Google Sheet or something like that and manipulate your data. So if you manipulate your data and you have to take the natural log versus the time in order to get a straight line, that means that you've got a first order reaction. If you go to plot your data and you don't need to take the natural log and you immediately get a straight line, that's called zero order reaction, and we'll talk about that more in a minute. So there's a special thing that you can do with first order rate kinetics, which is called the half-life. And the definition of half-life is the amount of time it takes for half of your substance to degrade or react. So you could have your first order rate kinetics, your natural log of A equals negative KT plus natural log of A sub naught. You know natural log of A after some time is going to be half of what you started, so you could just substitute A sub naught divided by 2 in for your Y term. And then your T1 half, once you simplify everything, you're going to get natural log of 2 because the A sub naughts are going to cancel out. And the natural log of 2 is just a constant. So your half-life equation is equal to T equals 1/2 times 0.693 divided by K. So T equals 0.693 divided by K. Well, some things might not be linear immediately, or they might not be linear when you take the natural log of the concentration of time. So the last option that you typically have in this class is second order, where rate is equal to rate constant times concentration of A squared, or to the power of 2, which means it's second order. And we're going to derive the second order integrated rate law. So we know that rate equals Ka squared. We also know rate equals change in concentration over time from the last video, and we could set these equal to each other just like first order. We're going to rearrange so that all of the A concentrations are on one side and everything else is on the other. And we're going to perform our magic integration, our magic calculus. And we could find that in order to linearize second order data, you have to take the inverse of concentration versus time. So the three things that you're going to look at to see what order it is run the experiment. If you plot your raw concentration versus time, straight line, that's zero order. If you don't get a straight line, take the natural log of the concentration over time. If that gives you a straight line, then it's first order. If that still doesn't give you a straight line, then you're going to want to take 1 over the concentration versus time, and if that should give you the straight line, and that means it's second order overall. So you've got 3 possible outcomes, and you're trying to get linear data. And remember, the slope of the line is equal to your rate constant. And the last thing we're going to briefly mention is zero order reactions, where rate is equal to just some rate constant, and it is not concentration dependent. So it doesn't really matter the amount of concentration you have, it's going to go at the same rate no matter what. We call that a zero order reaction. So there it is, you guys. There's the video on rate laws, first order kinetics, second order kinetics, and zero order kinetics, as well as the discussion about rate constant and how we analyze kinetic data. So if you like this video, smash the like button, send it to your favorite nebula, send it to your favorite planet within the solar system, and we'll see you in the next video.